Hi ladies, this is lesson 6.5. And in this lesson, we're going to look at graphing square root and cube root functions. So you have one key vocab term, and this is radical function. And a radical function is a function that's in the form y equals a times the square root of x minus h plus k. So if you look at this function, it should remind you of functions that we've worked with in the past, particularly the absolute value functions. If you think of the vertex of an absolute value function, you have h and k. Well, in this radical function, we also have an h and a k. And in your absolute value functions, think back to what the h and the k represented in your vertex. And the h stood for the x coordinate, and the k stood for the y coordinate. So h would be your horizontal coordinate, and k would be your vertical coordinate. Now we also have so this is a square root radical function, but we also are going to work with cube root radical functions, and that's going to be very similar, but it's y equals a times the cube root of x minus h plus k. So if you look at that key concept, here's your parent functions of square roots and cube roots. These we've graphed before, but pay attention to the domain and the range. So the domain of a square root function, x has to be greater than or equal to 0, because you cannot take the square root of a negative number. If you tried taking the square root of a negative number, you would end up with an imaginary number, and imaginary numbers are not in our graphing domain. We cannot graph an imaginary number, so we're looking at real numbers in this lesson. But if you look at a cube root function, the domain and range are all real numbers, and the domain and range are all real numbers because you can take the cube root of a negative number and still get a real number. Okay, so in this lesson, we're going to still, like we have been in the last few lessons, paying attention closely to domain, and now we're also going to look at range. So let's look at this first graph of a square root function. We're looking at the graph y equals 2 times the square root of x, and we're going to state the domain and the range. And we're going to compare the graph with y equals x. Y equals the square root of x. So I have graphed already y equals the square root of x. You can see that to the right. So you can see now my table of y equals the square root of x. Now again, you have to pay attention to the domain here, where x has to be a positive, or it has to be a non-negative number. So in this function, y equals the square root of x, domain is non-negative numbers. And if you think of what it means to be a function, so if this is a square root function, we can only have one output for every input. That means instead of having positive or negative 1 for y equals the square root of 1, we can only have positive 1. So our range is also non-negative real numbers. Okay, so as we go, as our x values increase, our y values are also increasing. Again, we can't have positive or negative 1, because if we had positive or negative 1 as an output for the square root of 1, then this would not be a function. Okay, so it has to be all non-negative real numbers. Now, if you look at the graph y equals 2 times the square root of x, and that's in the second graph here. Our domain is the same. Our domain has to be non-negative real numbers. And because our domain is non-negative real numbers, then our range also has to be non-negative numbers, or y has to be greater than or equal to 0. So if we look at this graph, 0, 0, 1, 2, and we rounded here, 2 times the square root of 2 is approximately 2.83. So somewhere around here. And then 3 is approximately 3.46. And then 4 is 2 times 2, which is 4. So there's our graph for y equals 2 times the square root of x. Now again, because we have the domain set at non-negative real numbers, our range is also going to be non-negative real numbers because you can't have 2 outputs for a single input. We cannot have 2 y values here for every single x value, because if we did, this would not be a function. So let's compare this function with the parent function. So we're comparing the orange function, 2 times the square root of x, with the parent function of y equals the square root of x. So if you look at these graphs, the graph of y equals 2 times the square root of x, that's a vertical stretch. It's taller than the original function for the same x values. Is y equals negative 1/2 times the cubed root of x, state the domain and range. Well, if you look at this parent function, you can take the cubed root of a negative number, you can take the cubed root of 0, and you can take the cubed root of a positive number, and all of those will give you real numbers. So here, looking at the domain of y equals the cubed root of x, the domain is all real numbers. Now, and you can see the graph in blue to the right. But now let's look at the graph of y equals negative 1/2 times the cubed root of x. And we've got our points here, negative 2 and 0.63. And negative 1 and 1/2, 0, 0, 1 and negative 1/2, and 2 and negative 0.63. So our graph of negative 1/2 times the cubed root of x, you can see that that's a reflection, first of all, over the y-axis, and it's also a little bit shorter. So it's a vertical shrink and a reflection. Or sorry, not over the y-axis, over the x-axis. But if you think of the domain and range, those domain and range remain the same. So any real number times negative 1/2 is still going to be a real number. So the domain is all real numbers. The range is also all real numbers because it's still a function. You only have one output for the cube, 1/2 times the cubed root of a number, whether that number is positive or negative. So it's a vertical shrink. If you look at the orange graph, it's shorter and it's a reflection. All right, take a couple minutes, pause the video, and do these next two examples on your own. So if you look at this first example, it's a cubed root, so you can have positive or negative values for x. So your domain is all real numbers, and your range is also all real numbers, because any output for y, depending on what your input is, could be any real number. So once you plot the graph, you should look at whether it's a reflection, vertical strength, or a vertical stretch. And in this case, it's a vertical stretch. It's not a reflection. The a value is still positive, just like it is in the parent function of the cubed root of x. And it's just a little bit stretched out vertically, so it's taller. So for every x value, your y output is larger. In the second example, y equals negative 2 times the square root of x, your x still has to be greater than or equal to 0. And again, since this is a function, for every input, you will have exactly one output. So the square root of 4, for example, is just going to be 2 because it's a function. It's not going to be positive or negative 2. So that means that your range, since you're taking negative 2 times the square root of x, so a negative number times a positive number is going to be a negative number, so your range is y is less than or equal to 0. And you can see the graph to the right. The purple one is the graph of y equals negative 2 times the square root of x, and the blue is just y equals the square root of x. Well, if you compare these two graphs, first of all, you have a reflection over the x-axis, which is this axis right here. And secondly, you also have a stretch. So this value, this negative value, gives you the reflection. And this a value gives you the stretch. So please jot down any questions that you have for this first part of graphing square root and cube root functions in the next video. We're going to look at graphs of radical functions as they relate to our y equals a times the square root of x minus h plus k, or the cubed root of x minus h plus a. So that's going to give us translations. So please watch the next video for more information regarding translations. But jot down any questions you have for this video and bring them to class with you. Thank you.